Hi there. Welcome to another edition of the Algebra 2 PLC. I'm John Chase, and I'm an Algebra 2 teacher at Richard Montgomery High School.
And I'm James Key with the MCPS math team. We received some emails asking us to focus this segment on certain questions from the exam review packet, and so that's what we're going to do. Let's go ahead and dive into problem 31, part D. In this problem, students are presented with the equation f of x equals e to the x. And in the series of questions around problem 31, they're asked to look at a variety of transformations and changes to that equation. In this particular part, they're asked to reflect the graph over the y-axis and to come up with an equation that describes that new graph. So I'm just going to think out loud in terms of how I would approach this problem. Along the way, I'm going to try to make use of what I know about reflections, and I'm going to try to make use of the fact that I already know the original equation for the original graph. So let's see where that leads. The point that's shown here has an x-coordinate of 8/10, and I'd like to be able to describe the y-coordinate that goes along with that. Well, using my knowledge of reflections, I know that the pre-image and the image are the same distance from the mirror there. And so, whereas this one is 8/10 of a unit to the right, the pre-image should be 8/10 of a unit to the left. In other words, the x-coordinate is negative 8/10. Now to determine the y-coordinate, I'm going to capitalize on the fact that I'm given an equation for the outputs. It says f at input is equal to e to the power of that input. So I'm going to write e to the power of this input. And I also know that when we do a reflection, the y-coordinate just isn't going to change. So whatever this y-coordinate is should be the same for both the pre-image and the image. So e to the negative 8/10. And now I've got a description of this particular point. I've got its coordinates. Let me go ahead and generalize that by using an arbitrary x value. All right, so same thinking. The pre-image should be x units to the left. And so the x-coordinate is negative x. And now we just go ahead and use the given formula, e to the power of that input. And then same y-coordinate before and after the reflection. So we'll use that y-coordinate again. And now we're well on our way to writing an equation that corresponds to this blue graph. So g of x is described by the expression e to the negative x. All right, and along with our discussion of transformations, John, do you want to talk about problem 32D, which involves a transformation of a logarithmic graph?
Yeah, I'd love to. These kind of go hand in hand. We're thinking about transformations, so let's take a look at this one. It's 32D, and it looks like intuitively this is a picture of the log base 2 graph, just shifted to the left 3 units. I think that because x equals 0 is normally the vertical asymptote, and now it seems like it's x equals negative 3. And to really confirm that, though, I want to actually take a look at these side by side. So I'm going to highlight a couple points. Let's choose a couple key points like this one here. This is 1, 0 on the original graph, and here we have over here negative 2, 0 on the new graph. Let's highlight one more point just to prove our point, so to speak. Here we've got 4, 2 on the pink dashed graph, and here we have 1, 2 on the blue graph, the new one, t of x. So it seems like 1, and this is confirmed by what we're doing here, that x equals 1 on the blue graph, the new graph, is acting like 4 on the old pink dashed graph. And likewise, that negative 2, x equals negative 2 on the blue graph, is acting like x equals 1 on the old graph. And to formalize what we mean by acting like, we want to kind of think about this. If we plug in 1 into the log base 2 function, it's acting like 4. That is, it's acting like something 3 bigger than itself. And we see that if we check our intuition there, that 1 acts like 4, that if we add 3 here, then the log base 2 of 4 is in fact 2. So that kind of confirms what we're saying. And then also, what about the log base 2 of negative 2 plus 3. Again, we're thinking that -2, from our little picture here, it seems like -2 acts like x equals 1 on the original curve. And in fact, the algebra over here confirms that. If we plug in -2 to our formula here, we're getting -2 plus 1 is 1, log base 2 of 1 is 0. That makes sense that 1 acts like 2, -2 acts like something 3 to the right of it, and in general, that log base 2 of x plus 3, it looks like we can kind of generalize on this pattern, that x in general acts like the thing 3 to the right of it. So in general, we have this formula for t of x. And if it works, I mean, we can check a couple other points. If it works, then we should go home happy.
Awesome. And John, I appreciate how you're emphasizing if it works, we can go home happy, because we don't want our students to get the impression that we are the answer keys, right? The math should speak for itself, and we want our students to develop an understanding that mathematics is a sense-making discipline, and the best way to find out if you're right is to test for yourself. And so I appreciate the way you said, hey, I can check a couple points. I've written down my best guess as to what the equation should be, but I've got these points right in front of me. I can see for myself whether my equation is correct. Let me just add one last thought here, just in keeping with the transformations-based approach. So I'm going to go ahead and just label this with an x-coordinate of x, and I'll reason through how to determine the y-coordinate. As John emphasized, we can tell that if we shift the new graph 3 to the right, we get the old graph. So in keeping with that, the x-coordinate on the corresponding point of the pink graph would be x plus 3. And then we can just use this formula right here, log base 2 of input, to describe the y-coordinate, log base 2 of input, where the input is x plus 3. And then the y-coordinate on this translation, since we translated 3 units to the right, the y-coordinate doesn't change. And so it should have exactly the same y-coordinate as this point.
Yeah, and that's another great way to explain. I think it's in general good to have be putting all of these transformations in the same place in your head as a student and as a teacher too. We want to have a holistic approach to transformations, not one that only applies to logarithmic graphs, for example. So I think that's an important idea, not just to communicate to in this exam review, but all throughout our course as we teach Algebra 2, that we want to have a good handle on transformations.
Absolutely. And I appreciate your attention to having a coherent framework, okay, so that it doesn't seem like we're doing different things when it comes to a dilation this way as compared to a dilation this way. If we're translating horizontally versus vertically, if we're reflecting over the x versus the y-axis, all of these things should feel like the same thought process, just in different contexts. One of the things that I've noticed, John, and we discussed this in our planning, is that for some students, in looking at the equation y equals f of x plus 2, some students feel like, you know what, it fits with my intuition that the graph is going to move up 2. Mm-hmm. Whereas for some students, when they see this expression, their intuition tells them that this should represent a rightward shift, and so it's like counterintuitive to them that it actually represents a leftward shift. So that's just like why I'm emphasizing using this transformation-based approach, so that in the end, it really is doing the same thing, whether we're translating horizontally or vertically. So just something to think about. We hope that this has been helpful to you as we talk through some of the solutions to the exam review problems, and we hope that you'll stay tuned as we continue to do that. Thanks for joining us.
Bye.